So 2.5, graphs and roots of quadratic functions. We are going to be talking about the types of roots that you can have with a quadratic function, how to recognize, when you're going to have a certain type, whether it's going to be real, imaginary, 1, 2, or none. And you're also going to learn how to convert between the different forms of a quadratic, because it's not just about standard form when it comes to quadratic. There's other forms as well with quadratic functions. So we'll start with the roots. The discriminant is a piece of the quadratic formula that tells us information about the roots of an equation. The discriminant, which is usually represented with a delta symbol, is b squared minus 4ac. That part that's underneath the radical in quadratic formula. That alone is that one piece that basically will tell us the types of roots that we're going to have. If b squared minus 4ac is greater than 0, whatever a, b, and c are, if we plug it in, that value is greater than 0, then that means we're going to have two different real roots. Okay? Two different ones. So like -2 and +4. Okay? Or in the case of our problem of the day, -18 and +17. Another word for different is distinct. Ivy likes to use this word often. So it might say that, this quadratic has two distinct roots or two distinct zeros. That means they're different. That means the discriminant is greater than 0. If the discriminant is equal to 0, then you have two equal roots. In other words, a double root. That essentially means that the value doesn't just show up one time, it actually shows up twice, but it's the exact same value, hence the double root. And lastly, if the discriminant is less than 0, then you won't have any real roots. You'll have imaginary ones. That's when I comes into play. Now with this level of IB on the SL level, you won't have to worry about dealing with any imaginary roots, okay? And so, you pretty much just got to be able to work with the first two, but the last one's also good to know as well, just in case. So we're going to determine the nature of the roots for each of the equations using b squared minus 4ac. So since the discriminant is b squared minus 4ac, we need to identify what is A, what is B, and what is C, so that way we can determine the nature of these roots. What is B and A? Is 6. What is A? 9. And what is C? 1. It's not equal to anything. It is literally just the plugging of the numbers. It's an expression. So from there, you just work everything out. 6 squared is 36. Minus 4 times 9 times 1, which is another 36. 36 minus 36 is 0. If the discriminant is equal to 0, that means we have what?
Two equal roots.
We have two equal roots, or a double root. Now in B, is this in standard form? We got to get in the standard form in order for us to be able to find the nature of these roots. So how do I get into standard form? What do I need to do?
Times x both sides.
Times x to both sides. Now when I multiply both sides by x, I'm multiplying everything by x. So that turns into a 3x squared minus 5x equals 4. Make sure you distribute that x to both pieces on the left-hand side. And then?
Bring the 4.
By doing what?
Minus 4 on each side.
Very good. So now my quadratic is in standard form. What's B?
-5.
I'm going to square that. Minus 4. What's A?
3.
And what's C?
-4.
-5 squared is 25. Minus 4 times 3 is 12. 12 times -4 is
-43.
And 2 negatives make a.
+3.
So then my discriminant is going to be 73, which means what type of roots are we going to have?
2 different real roots.
2 different or distinct real roots. That's how we use the discriminant. Okay, that's how we use it. We want to make sure it's in standard form, so in that way we can make sure we can work with it. But realistically, that's probably not the types of problems that IB is going to give you. They're going to be more like this. They're going to be more like this. So go ahead and get this one down. So it says find the values of k for which the equation 2x squared minus kx plus 3 is equals 0 will have 2 different real roots. This is more like an IB problem. First off, it says find the value, parentheses, s. That means you can either have one or more than one value of k that makes this quadratic have 2 different real roots. The key thing here is that it tells you that you have 2 different real roots. 2 different real roots means discriminant. The discriminant is going to be what? If you have 2 different real roots.
Is that greater than 0?
It's going to be greater than 0. So knowing that, based off of the fact that you have 2 different real roots, you can set up the discriminant and essentially set up an equation here to find the value of k to make this a true statement. So we know that the discriminant again is b squared minus 4ac. That's going to have to be greater than 0. Looking at this quadratic, that's already in standard form. What's the value of b?
-k.
I'm going to square that. Minus 4, what's a?
2,
What's c?
3.
This has to be greater than 0. So when I square this and simplify, I'm going to get k squared minus 24 is greater than 0. Now, quadratic inequalities work a tad bit differently than they do quadratic equations. Okay, you still go about solving it the same way, but that inequality causes you to have to realize that the values you get, you're talking about a range of values now. That whatever you plug in for k, and you subtract 24, have to be greater than 0. So when you solve this, the way I kind of do it is I remember that this is an inequality, and I'm essentially going to solve for k like I would if it were an equation. So I'm going to change my color so then that way I can keep in mind that this is an inequality, not an equation. But I'm going to treat it like an equation to solve for k. So that means that if I temporarily treat it like an equation, I solve for k, I'm going to add over 24. Then I'm going to take the square root. And when I take the square root, we can't forget, we're going to have what?
Plus or minus?
Thank you, plus or minus. Anytime you take the square root of an equation, it's plus or minus. Same thing applies with the inequality. Now, the square root of 24 can break down to be what? Like simplify that radical.
I don't remember.
What 2 numbers multiply to give you 24?
4 and 12.
4 and, not 12.
My bad, 6.
4 and 6. 4 is a perfect square, is it not?
Yes.
So then it becomes 2 square root of 6. So what this means, it doesn't mean that k is positive 2 root 6 and k is negative 2 root 6. That means is that on a range of values for k, the values of k that are going to make it so that I have 2 different real roots are either going to be less than negative 2 root 6, in between negative 2 root 6 and positive 2 root 6, or greater than 2 root 6. That is the impact that the inequality has on a quadratic when you're solving quadratic inequalities. What I've essentially done is I've taken these values and I've put them on a number line to essentially test to find out, okay, well, what values actually what values for k are actually going to be greater than 0 when I plug it in. So I kind of choose points that are in between or in each one of these intervals. A number that's less than 2 root 6, negative 2 root 6. Well, I originally had it from the square root of 24. Negative square root 24. What number is less than negative square root 24?
Negative square root of 25.
And what's square root of 25?
5.
So if I plug in negative 5 into this inequality, that becomes 25 squared minus 24. Is that greater than 0? Yes, it is. So because negative 5, when I plug it in, is greater than 0, that means that all the values that are to the left of negative 2 root 6 are going to provide a solution that is going to be greater than 0. So if I were to choose negative 6 or negative 10 or negative 20 and I plugged it in, when I square it and then subtract 24, it's always going to give me a value that's greater than 0, which means it's always going to be a value that gives me 2 distinct real zeros. What's the number in between these two?
0.
If I plug in 0, 0 squared minus 24, is that greater than 0?
No.
No. So that means all the other numbers that lie in between, like positive 1, negative 1, positive 2, negative 2, they're not going to work. What's the number that's bigger than 2 root 6 or bigger than the square root of 24?
Square root of
25. I mean 5.
Which would be 5, right? When I plug 5 in, is it going to be greater than 0 or less than 0?
greater.
So because all the values greater than 2 root 6 and all the values less than negative 2 root 6 work, the values of k that will give me 2 different real roots are all the values that are greater than 2 root 6 and all the values that are less than negative 2 root 6. And that's my solution for this problem. Okay? But that's more like the type of IB problem that you're going to get, okay? Be able to recognize that it's going to be greater than 0, less than 0, equal to 0. I might have to do the testing of the number line. If it's an inequality, if it's an equation, it is those values, okay? Don't forget your plus and minus. Now let's talk about the graphs of quadratics. There's different forms: standard, vertex, and factored or x-intercept form. We'll talk about standard first, and then we'll go to the other ones. In standard form, we know that it's ax squared plus bx plus c equals y or equals 0, depending on whether or not we're like solving it or if we're trying to do other things with it. But this in standard form, the graph will always cross the y-axis at 0, c. So whatever the value of c is when you're in standard form is your y-intercept, okay? To find the equation of the axis of symmetry, you would use this equation right here, x equals negative b over 2a. This is one of the only things that's actually in your reference booklet for functions. Like one of the few things that like they give you, everything else you're gonna have to know. Okay, so discriminant, I don't believe they give you anything about the discriminant, so you gotta know all those rules about discriminant. But they'll give you the equation for the axis of symmetry, and the thing is, it's an equation. So you have to have the x equals, otherwise it's wrong, okay? Now the axis of symmetry is an imaginary line, imaginary vertical line that goes through the vertex, making a parabola symmetrical. So when you have a quadratic, it is in the shape of a U. The axis of symmetry is a vertical line that goes straight through the vertex that splits your parabola in half equally. And the equation to find that is negative b over 2a. That equation is also how you find the x-coordinate of your vertex. So whatever the axis of symmetry is, that is also the x-coordinate of your vertex. Before we move on to the next form, to find the y-coordinate of your vertex, just like to find any y-coordinate, you always take the x value and you plug it in. So if you wanted to find the y-coordinate of your vertex, then you would just plug in that x value into your original function. That's how you find the vertex. So in standard form, the C is your y-intercept. Your axis of symmetry equation is x equals negative b over 2a. That is also the x-coordinate of your vertex, and you plug it in to get the y-coordinate of your vertex. So a few features about standard form. Vertex form, that's another form. Vertex form is in the form of y equals a, parentheses, x minus h squared plus k, where the vertex is at h, comma, k. All right, that's why it's called vertex form, because when it's in this form, your vertex is essentially given to you. This is also like the makeup for a quadratic when we were doing transformations, okay? Remember, anything on the inside moves the graph left or right, anything on the outside moved it up or down. So that HK represents exactly what happened. Because normally the vertex of a parabola is at 0, 0. But when it's been moved H units one way and K units another way, now that's the new vertex. You can go from one form, standard form, to vertex form through the process of completing the square, okay? Do you guys remember the steps of completing the square?
C on the side.
You get C by itself.
Yeah.
Before we could divide B by 2, we have to, you want to make sure A is equal to 1, you want to divide B by 2 and then square it and then add it to both sides, okay? Now, you can definitely do that here, okay? You can kind of leave the y out, subtract the 4 over, and do the process. You just have to bring that value back. But I want to show you how to do it with everything on the same side. So when you do it with everything on the same side, you'll have a square beside your A and your B term, and then you'll have a square on the side of your C term. But because you're doing everything on the same side, you don't want to add it, you want to subtract it. So it's a little bit different, okay? You don't want to get C by itself. You do want to make sure that A is equal to 1. You do want to take half of B and square it. But instead of adding to both sides, you'll add for one and subtract for the other. So, is A 1?
Mm-hmm.
So now let's take B. What's B?
6, negative 6.
Divided by 2, which is?
Negative 2.
And then we need to square it. What's that?
9.
That is the number that will add in the first box, but will subtract in the second box. And then we'll factor and simplify just like we did before. X squared minus 6x plus 9 can factor down to be x something something squared. What's on the inside? Positive or negative?
Negative.
Remember, the value you got when you took half of B is always the value that goes in that parenthesis. And what's 4 minus 9?
Minus 5.
And there's your vertex form.
Oh.
A, x minus h squared plus k. Now again, you could have subtracted the 4 over. You could have still completed the square like normal. It's just that you would have had to bring that 5 back over to the other side to get it in vertex form. So in this problem, our vertex is going to be 3, negative 5, because remember it's always the opposite of what's on the inside. That means move right 3, down 5. And it asks us to sketch this function. Okay, so that's what we're about to do. We're about to sketch it. I definitely need the vertex in order to sketch this. What's on my next page? Another problem? I think so, yeah. So when I sketch this, all I really and truly need is the vertex. I do have my y-intercept, which can be helpful. But does anybody remember the pattern when it came to graphing a quadratic?
Wasn't it where the vertex is? It goes like on both sides, up one, right one, and then it went like up 3, right 1.
Very good. That is the pattern for any quadratic. If you're like, what do you mean? That means that every point from the vertex, if you went up 1 and then to the right 1, that is your next point on your quadratic. From that point, if you go up 3 and right 1, that's the next point. And because of quadratics are symmetric, you can just copy that same point across your axis of symmetry. Of course, this changes, there's a vertical stretch, but it only changes your y's. There's no vertical stretch here. We're graphing y equals x minus 3 squared minus 5. So I plot my vertex at 3, -5, and I'm going to go up. I'm going to go up because my a value is bigger than 0. Anytime your a value is bigger than 0, the parabola opens up. If it's less than 0, it opens down. So from here, I'm going to go up 1 unit, right 1 unit. That's a point. Then I'm going to go up 3 units, right another unit. The next value in this pattern is up 5, right 1. So then I can go up 5 units, 1, 2, 3, 4, 5, and right 1. And that is the right side of my parabola. Yes?
I don't really understand how you got the point.
Okay, so this right here, this is something that we teach in Algebra 2 and also in pre-cal about how to graph a quadratic easier. This is just the pattern of every quadratic that has an a value that's equal to 1. You just go from the vertex, you go up 1 unit to the right 1 unit, and then this point is a point that's actually on your quadratic. And then from that point, you go up 3 more units and over 1, and that's another point. Up 5 units over 1, that's another point. So all these points are actually points on my quadratic. Of course, you can make a table, plug in values, but that's going to take some time. We need to be quick about this. Don't forget the axis of symmetry. That is a vertical line that goes straight through your vertex. So x equals 3 will be my axis of symmetry. I can just copy those points over the axis of symmetry to get the other half. So this one's going to be here. This one's going to be over here. And this point's going to be here. Which makes sense because wasn't my y-intercept, when it was in standard form, +4 in this problem?
Yes, ma'am.
Yes, it was. So that's how we would graph our quadratic in vertex form. Find the vertex, plot it, apply the pattern. It opens up again because a is greater than 0. And it does have that y-intercept of 0, 4, which I knew from standard form, which was what the problem originally gave us. Let's do another one. We're going to do this one. Y equals x squared minus 8x plus 18. We're going to write it in the form again. Remember, if I want to complete the square on the same side, I have to add or subtract here.
No,
And then on this side, I'll have to subtract. Is A 1?
yeah.
Yes. Let's take half of B. What's B?
No, -8.
What's half of -8?
-4.
Square it. What do you get? That's the number that I'll add here, but I subtract here. This can be read in the form of x plus a number, or x minus a number squared. What's the inside?
Negative.
X minus 4 squared, and then on the outside?
2.
What's the vertex of my quadratic? 4, 2. So that means from the origin where the vertex originally was, I moved to the right 4 units and then up 2 units. Is this parabola going to open up or is it going to open down? And I know this because A is greater than 0. So when I go to graph this, where's my axis of symmetry?
Where it's 4.
And we always want to make sure that we write it as an equation. X equals 4 is my axis of symmetry. It's always a dotted line. I plot my vertex at 4, 2. And what's the pattern?
Up 1, right 1. Up 3, right 1. Up 5, right.
And so then I can just copy that over. I have a y-intercept at 18, so I bet if I kept going with my pattern, which would be up 7 over 1, I would finally hit 18. The point is it's the pattern. Up 1, right 1. Up 3, right 1. Up 5, right 1. And so I'm basically going from each point. So from the vertex, I go up 1 unit, right 1 unit. That's one of my points. Then from that point, I go up 3 more units, 1, 2, 3, over 1. Then from that point, I go up 5 units, 1, 2, 3, 4, 5, over 1. And then that's how I get the next point. And it works that way every time on a parabola that has 1 as its a value. And it's just a shortcut way to graph a quadratic. Like what I really could do is I can plug 5 into the original problem, right? 5 squared is 25. 5 times -8 is 40, then plus 18. So that would give me -15 plus 18. So then that's at 3. 5, 3 is a point that's on my parabola. That's where this one is. It was at 5, 3 because it was up 3 units and over 1. But I could also get there by just doing up 1 over 1. I could do the same thing with 6. I could do the same thing with 7, but I would get these points that follow this pattern. So this is the pattern. This is helpful in the graphing process instead of picking points and plugging in. Well, it's quicker. If you notice, the a value between standard form and vertex form will always stay the same. That should never change, okay? When the a value is not 1, like in this case, okay? It does affect your process a tad bit because now that you have an a value, you have to factor that a out, or you basically have to make sure that you know, the a inside your parentheses before you do half of b and stuff. You know, that still needs to be 1. So when I look at this problem, -2x squared minus 12x plus 7, a is not 1. Now, normally when we solve, we divide the a. But because I'm going from one form to the next form, the A value has got to be the same between standard form and vertex form. So instead of dividing everything by that value, I'm going to factor out that A value instead. So what that means is I'm going to take out that -2, that A value, from not every term, but the first 2 terms. Okay? So when I have an A value, I factor it out, I don't divide it out, and I'm only factoring out the first 2 terms. So when I do that, that gives me an x squared plus 6x. Again, I only take it out of the A and the B term, not the C. And I still have the plus, and I still have the minus. That has not changed. So when A is not equal to 1, you factor out the A value from the first 2 terms. So from the AX squared value and from the BX. Then you still have your adding, you still have your subtracting of your box. I still have to take half of B and square it. What's B now? The new B.
6.
What's half of 6? And square it, what is that?
9.
That's the number I have to add here and subtract here. Now when I go to write it in vertex form, the -2 is on the outside. That's your A value. Oh, sorry. I forgot something here, and I do apologize. I need to go back a little bit. I did forget something. So video online, I did forget something. I knew I was going to do it, so my mistake. Unfortunately, this is another thing that's a little bit different from when there is an A value. You take half of B, you square it, and you get your value. That value goes in this first box. But the value that goes in that last box, the value that you subtract, is the product between your A value, and the value in the box. You have to multiply whatever A was that got factored out by the value you got when you took half of B. So what's -2 times 9?
-18.
So I'm going to have a minus a -18. That is another effect that actually having an A value has when you have to write it in vertex form. So you factor A out of the AX squared plus BX term. You still take half of B and you square it, but the value you subtract is the product between A and that first box. Okay? Or the value you get when you take half of B and square it. I should say that instead. Now I can actually write it in vertex form. So it's going to be -2x plus 3. Again, it's the value you get when you take half of B. And then what is 7 minus a -18? 25. And there it is in vertex form. What is my vertex?
Maybe 3.5.
Is this graph going to open up or down?
down.
And I know this because of what reason?
Your A slash B.
Very good. And because it opens down, the pattern is now going to be up 1 over 1, up 3 over 1, up 5 over 1, because it now opens down. So instead of all my ups, I'm going to go down. And this 2 vertically stretches my graph. So my pattern that normally, again, is up 1 over 1, up 3 over 1, up 5 over 1, now becomes down, because it's opening down, it's negative, but now it becomes down 2 over 1. Because that A value of 2 vertically stretches it. That means I multiply my y's by that value. It's no longer up 3, it's now going to be down because I have to multiply by 2, but I still go over 1. And then I'm going to go down, but still go over 1. So that's how your A value affects your graphing. So 325 is going to be my vertex. I have my axis of symmetry. That's a little off. My point is a little off. And now I'm going to go down 2 over 1, down 6 over 1. Then I'm going to go down 10 over 1. Was the y-intercept 7 from the original standard form? Yes, it was. So there you go. Pattern works every time. You may have to alter it depending on your A value, but it will work every time. Then you just copy those points over. So x-intercept form, also known as factor form, is the last way that you can write a quadratic. It's called x-intercept form because it actually tells you, or you can pull out your x-intercepts very easily from this particular form. It's known as factor form because it looks like a quadratic has been factored, okay? So that in general, the form is y equals a x minus p times x minus q. Okay, just like it looks just exactly how it would if we were to factor with the GCF, okay? That A value is the same A value in standard form as it is in vertex form. Your x-intercepts are at P0 and Q0, so you do need to do the opposite of whatever's in those parentheses. And your axis of symmetry is the halfway point between your x-intercepts. So you do P plus Q divided by 2. Again, it's still in the form of an equation, so make sure you have that x equals, otherwise it's not going to be counted correctly. And they will bold equation in the question to remind you that it's supposed to be an equation. You need to have that x equals, otherwise it's wrong. Okay, but that's x-intercept form. So as you can imagine, to go from standard form to x-intercept form, we essentially need to factor. I have a function, x squared plus 3x minus 10. I'm going to write in the form of f of x equals x minus p, x minus q, and then we're going to sketch. As you should be able to see, the A values from x-intercept form and standard form are the exact same. They're both 1. And so all you need to do from here is you just need to ask yourself what two numbers multiply to give you negative 10 that add together to give you a positive 3. So then be x plus 5, x minus 2. There it is, in factored form. My x-intercepts are what? Remember, they're P0 and Q0. So what's the value of P?
-5.
-5, 0, and?
Q.
If you ever question it, you know you can always set each factor equal to 0 and actually solve it, because that's what we did when we were solving quadratics. When we're solving quadratics, we are finding those x-intercepts. We're finding those points where it crosses the x-axis. What's my axis of symmetry? You add P and Q and divide by 2. -3/2, because again, you add P and Q and divide by 2, so that's going to be x equals -3/2. So that means when you go to graph it, yes, you can have fractions as vertices and axis of symmetry. You know, we're beyond, it's always got to be a whole number. Okay? So -3/2 is -1.5. And unlike, you know, vertex form, of course we can use the pattern, of course, but I have both of my zeros at 2, 0 and -5, 0. All I need now is my actual vertex, because I just need to go through those 2 points. I know the x-coordinate of my vertex is -3/2 because it is the axis of symmetry. It's the same value. How do I find my y-coordinate? Well, I already found that out. It's -3/2. How do I find the y-coordinate now that I know the x? How do I find any y-coordinate when I know the x?
Oh, you plug it in.
To the
X.
of the
Formula.
the original. I plug in the x value into the original to get the y-coordinate of my vertex. Okay? This would probably be non-calculator as well. Okay? -3/2 squared is what? 9/4. 3 times -3/2 is what?
-9/2.
Very good. -10. In order to be able to subtract these from each other, I need to have a what? What's the common denominator going to be?
4.
4. That's the smallest one. This one stays the same, but 9/2 turns into what over 4?
18.
And 10 turns into what over 4?
40.
So what's 9 minus 18 minus 40?
Is it -67?
No, too big.
Too big.
9 minus 18 is a -9. -9 minus 40 is -49. So it's not pretty, but it gets me where I need to be. It's like all the way down here, because that's going to be like -11, -12. So all the way down here at -12 something, that's my vertex. Then all I have to do is just go through my x-intercepts, because I already have them. No need to do the pattern. I have my x-intercepts. They just have to go through those. Let's do the last one, working with the different forms. Okay, this one is gonna have an A value. So for this one, we know that we have to get in to a factors form, and the A needs to be factored out. Now, the one downside about this particular problem is that there's no GCF, right? Because if it was a GCF, we would take it out, and boom, that'll be our A. So for this one, it's going to kind of go against, the things I've taught you when it comes to factoring. But let's factor this, right? Slide divide bottoms up. We multiply 2 and 3 together, 2 and negative 3 together. What does that give us? So we're looking for two numbers that give us -6 that add together to give us. What are those two numbers?
-3, 2.
Okay. Now, this is why I said this kind of goes a little bit against what I've told you guys. So we write them in our factors, and then we would do divide and bottoms up, right? So we're going to divide just like we normally would. So because there's an A value, we would divide. And instead of simplifying, we are going to bottoms up. And this is why, okay? Because we're going to bottoms up on both without simplifying. And the reason why we want to do this is because our A values need to be the same. They have to be the same. So what we're going to do is we're going to take out that A value, which we already know needs to be a 2, from both parentheses. Sorry, I made a mistake. I didn't mean to simplify, like force a habit. Sorry, there should be a 2 here. What we're going to do is we're going to factor out that A value, that 2, from both sets of parentheses. When we do that, when I take a 2 out of 2x, that gives me what?
X.
When I take a 2 out of a 3, what does that become?
3 over 2.
When I take a 2 out of a 2x, I know that becomes an x. But when I take a 2 out of 2, that becomes a. So this is your factor form. In the form of y equals a, x minus p, x minus q. Again, this goes against everything that means to be factored, but this is the factor form. My x-intercepts are what?
Three over 2, 0, and 1, 0.
Careful.
-1. Wait, 1 negative.
Because it's the opposite. Remember you said this equal to 0 and solve?
Oh.
My axis of symmetry is the halfway point in between them. So that's going to be 3 over 2 plus a -1 divided by 2. How do I add a fraction and a whole number together?
You did that thing.
But before I get to that divide by 2 part, how do I do 3 over 2 plus a -1?
Oh, you try to.
Which would be what? 2. So this becomes 3 over 2 minus 2 over 2, which is what?
1 over 2.
So this becomes 1 over 2, 1/2 divided by 2. What's 1/2 divided by 2? 1/4. So my axis of symmetry is x equals 1/4. And then of course you could graph this using your axis of symmetry, your vertex, your x-intercepts, and your y-intercepts. But we'll hold off on that one. The purpose of this example is to show you how to do it when you have an A value and you have to factor it out. Now, normally there'll be a GCF, so always check for your GCF. But if not, you kind of have to go against what you know about slide, divide, bottoms up a little bit. So then that way you can factor out that A value so it can be equal. And those are your different forms. Factor, x-intercept form, vertex form, standard form. Each one has its own different features that you can find out about the graph of a quadratic. and the discriminant, which is telling you about the types of roots, types of zeros, types of x-intercepts you're going to have.